Good morning, students. So, today we are going to start Unit 4. The first topic of Unit 4 is basically Raman spectra. And first, we will like to discuss what is Raman spectrum and how does it differ from the Rayleigh scattering. Okay, so when a beam of monochromatic light from a visible portion of the spectrum is passed through a transparent medium, a portion of the light is scattered in all directions. The frequency of the scattered rays is the same as that of the incident beam. Means a light come with the incident frequency is suppose nu y, and it when it passed through a transparent medium, its intensity remains same as before it passed through the medium, and this is known as basically Rayleigh scattering. But a careful spectroscopic examination of the scattered rays reveals some faint lines other than that of the Rayleigh scattering. Means we generally observed the light when passed through this medium, the same frequency radiation is scattered in the all direction, but at the same time very slightly different frequency lines are also observed, though their intensities are very less. So this is small portion of the rays are called scattered with this different frequency. This was first observed by Raman in that phenomena was first observed by Raman, that is C.V. Raman in 1928, and the phenomena is called as Raman scattering. So suppose this is the frequency and this is the spectrum that is obtained after passing through the light, and the same frequency light that is basically nu zero I have not written here. So when light passing through this medium and giving the same frequency scattered radiation, that is called Rayleigh scattering. And apart from the Rayleigh scattering, in both the sides, in lower frequency side and the higher frequency side, some faint lines are also observed. So these are the Raman lines, and these Raman lines are called anti-Stokes lines, and these are called Stokes line. Later we will discuss about Stokes and anti-Stokes lines. Okay, so the difference between the frequency or wave number, so delta nu in energy unit equal to nu zero minus nu r, where nu zero for Rayleigh scattering and r is for Raman scattering. Okay, this is energy unit and this is in spectroscopic unit. For a given substance, the Raman shift is found to be independent of the frequency of the incident radiation. That means suppose you are using different frequency for the same substance to find the difference between the frequency of Rayleigh scattering and Raman scattering, or incident frequency and Raman's frequency, and accidentally you will find that every time you will get the same delta nu bar values. Okay, so that is, it has the same value for the different frequency of the incident light. This difference is a characteristic of the substance and is found to be equal to its vibrational and rotational transition. Means it depends only the respective vibrational and rotational energy level. So once you have not changed the substance, that means every time you will get the same energy change. Whatever your incident frequency, it will automatically adjust the Raman scattering also, and that ultimately give you the same delta nu bar value. So this is the delta h nu y incident frequency, and when it passed through this transparent medium, some light scatter with the same frequency nu y and some light scatter with the nu s frequency. Nu y frequency of the incident light and nu s. So Raman effect, or a change in energy of the scattered photon, is due to the exchange of energy between the photon, that is incoming photons, and the molecule of the material. Suppose the molecule before the excitation or in interaction with the light have energy E1 and supplied energy, that is incident light h nu y, and after this interaction molecule becomes having energy E2 and scattered light have energy h nu s. So according to the energy balance equation, left side energy, total energy should be equal to the right side total energy. So E1 plus h nu y equal to E2 plus h nu s. Now I will suggest student to follow this equation, not this equation. So E1 minus E2 by h equal to nu s, that is scatter frequency, minus nu y, and that is called delta nu. Okay, so if the molecule gains energy, that means molecule gains energy means the scattered photon should have energy less. Okay, the scattered light is called the Stokes-Raman scattering. That means when E1 is less than E2, then delta nu is less than 0, and this is called Stokes-Raman scattering, and it is more intense. If the molecule lose energy, that means if E1 is greater than E2, then delta nu higher greater than 0, and this radiation is called anti-Stokes Raman scattering. If the molecule lose or gain energy only in the rotational level, then it is called rotational Raman effect, and if the molecule lose or gain energy only in the vibrational level, then it is called the vibrational Raman effect. Now I would like to suggest one thing, why your Stokes-Raman lines are generally more intense than anti-Stokes-Raman lines because the Stokes-Raman lines are nearly 100 times more intense than the anti-Stokes-Raman lines. Is because the fact that the molecules are generally, if the molecule before interaction with this incident light is already present in the vibrationally excited state, okay, then they give measure, then there is a possibility to give some anti-Stokes-Raman lines. But we know that the population of the molecule depends on the Boltzmann type distribution, that is number of molecule in the excited state divided by ground state equal to e to the minus e by kt. Since the population in the excited state is very less, that as we know in normal condition or temperature, so the intensity of the anti-Stokes-Raman lines have nearly not only is less, and hence only few lines are generally which are more intense are observed. Okay, so however